We're going to take a look now at another piece of the mean value theorem, and we're looking at increasing and decreasing functions. There will be definitions of both an increasing and a decreasing function in this video, and then also a theorem to match with those. So we begin with this, and it's really more of a definition to give us a ground on which we're going to see how the mean value theorem applies. We want to define what it means to call a function increasing and to call a function decreasing. So let's look here. Let f be a function defined on an interval I, and let x1 and x2 be any 2 points in the interval I. Definition 1. We're going to say that f increases on I, on the interval, if for those two x values, x1 less than x2 implies that f of x1 is less than f of x2. And let's see what that means graphically. So here's an xy grid, and I'm going to sketch in just an arbitrary function that we know is increasing from our pre-calculus days, that increasing informally means that as we travel left to right, the graph is moving upward. So let's let two x values be defined on this interval here, and x1 is less than x2. That was the first part of this definition. So what we want to say here for a function increasing is, as long as this is true, as long as the first x value is less than the second x value, then the first y value, or the y value that goes along with x1, will be less than the y value that goes along with x2. So the first x less than the second x implies that the first y is less than the second y. And we can see here that, yes, that does indeed ensure that this function travels up from left to right. I'm going to write in INC here for increasing. Secondly, f decreases on the interval I if x1 less than x2 implies that f of x1 is greater than f of x2. Let's see that graphically as well. So if we consider a function that is decreasing on an interval, we know from our pre-calc days that means that the function is traveling downward from left to right. We pick any two x values, and as long as we label them so that the first x value is less than the second x value, then this time around, the first y value will be greater than the second y value, and this ensures that we are talking about a decreasing function. So now that we have well defined what it means to be increasing and decreasing on a particular interval, let's look at a corollary. The mean value theorem enables us to identify exactly where graphs rise and fall, exactly where they rise and fall. Functions with, here's the key part, functions with positive derivatives are increasing functions, and functions with negative derivatives are decreasing functions. That's a pretty awesome corollary, and it's proven with the mean value theorem. Here it is more formally. Let f be a continuous function on a closed interval a to b and on a differentiable interval open a to b. 1. If f prime is positive at every point in the interval, then f increases. And if f prime is negative at each point in that interval, then f decreases. Let's look at that graphically one more time. Here's that same arbitrary increasing function that I drew in the last slide. Notice that every single point, if I were to make a point on the graph and sketch in a tangent line, that tangent line has a positive slope everywhere. There's nowhere that I could find on this interval of increasing in this function where the tangent line would be anything other than positive, because all of the tangent line slopes would have to be greater than 0. For a decreasing function, let's look at it the other way. Pick a point, check out the tangent line, estimate its slope, that's negative. Pick another point, sketch in a tangent line, estimate the slope, yeah, that's going to be another negative value. So big takeaway here. If f prime is positive, then f increases. If f prime is negative, then f decreases. There's a lot we can do with that. Let's see an example of a real function. So here's a function we're all familiar with, y equals x squared. This function is decreasing on the interval negative infinity to 0 because y prime is 2x, and 2x is always negative on the interval negative infinity to 0. So let's take a look at this. I'm going to do part A, the decreasing portion, in blue. So that would be all of the points on this graph from negative infinity all the way up to 0, and take a look at any possible point and sketch of a tangent line. The slope is negative. A point, sketch of a tangent line, the slope is negative. A point, sketch of a tangent line, the slope is negative, continuing all the way until we get to just to the left of 0. So we are decreasing on that interval. Likewise, let's do part B in red. F is increasing on the interval from 0 to infinity because y prime is 2x. And again, we could find that derivative real quick. Y prime equals, by the power rule, 2x. And 2x is always going to be positive on the interval 0 to infinity because we'd be plugging in a positive number, multiplying by 2, and that would still be positive. So let's graph this part in red. Here's our increasing section of the graph. And if we take a look at any random point along that curve and sketch in a tangent line, what we see is those tangent lines have positive slopes. So one more time in review, if f prime is positive, then we are increasing on the interval, on, we'll say just I for the interval. If f prime is negative, then we are decreasing on, there's a G there, on that interval. All right, now let's try example 15 from the exercises. So in this example, we want to use analytical methods. That means by hand using algebra and calculus to find the local extrema, to find the intervals on which this function is increasing, and see the intervals on which this function is decreasing. All right, so let's take a look at f prime first. We know we need to look at the derivative. So f prime of x by the power rule is 5 minus 2x. Now we know that this function is going to be increasing where the derivative is positive, and we know it's going to be decreasing where the derivative is negative. So let's take a look first at 5 minus 2x and go with where that is positive. So let's continue to solve here. So we'll subtract 5 from both sides. We'll have negative 2x is greater than negative 5. We'll divide both sides by a negative 2. We'll have x is less than positive 5 halves, because once we divide by a negative, that greater than sign flips over to a less than sign. So we're negative on the interval from negative infinity to 5 halves all the way included, and that means that since the derivative is positive, we are increasing here, increasing. And then we want to look at where 5 minus 2x is negative. So we solve this, subtract 5 from both sides. Negative 2x is less than negative 5. Divide both sides by negative 2. Now we have x is greater than 5 halves. So on the interval from 5 halves to positive infinity, we are decreasing because we know that the derivative is less than 0 or negative. So there we have it. We've answered part B and part C. What I haven't answered is part A, the local extrema. And because we switch from increasing to decreasing at x equals 5 halves, we can kind of envision then that we've got a top of a hill on our graph, and that's going to be then a local maximum. So I'm going to give that as an answer as well. Local maximum at x equals 5 halves. So we have this, we have the function decreasing, we have the function increasing. All right, let's go next to another example. Determine where this graph rises or falls. So where is this function f of x is x cubed minus 4x increasing, and where is it decreasing? So very similar to what we did in the last example. First, we want to take a look at the derivative. F prime of x is equal to 3x squared minus 4. And then we know that the function will be increasing when 3x squared minus 4 is positive. And we know that the function will be decreasing when 3x squared minus 4 is negative. So let's go through and solve these. So first we would want to add 4 to both sides of this function. That gives us 3x squared is greater than 4. Then divide both sides of that function by 3. So now we have x squared is greater than 4/3. And once we take a square root of both sides and factor in that we are introducing that square root, we need a plus or minus, we end up with this solution works if x is less than negative square root of 4/3 or x is greater than the square root of positive 4/3. Now we know this function is decreasing when 3x squared minus 4 is less than 0. Let's change that to a less than if it's negative. So then we end up with 3x squared is less than 4. We end up again with x squared. This time it's less than 4/3. And when we factor in the plus or minus there, we end up with x is greater than negative 4/3 in a square root, and x is less than positive 4/3 in a square root. So this is actually on the interval. Negative square root of 4/3 is less than x is less than square root of 4/3. So altogether in interval notation, this function is increasing on the interval from, let's see, I'm going to take care of this one first, negative infinity to negative square root of 4/3. And we'll include that one there. And it's also increasing on the square root of 4/3 positive to infinity. And then we are decreasing on the interval from, let's make that into an included, there we go, a bracket, negative square root of 4/3 to positive square root of 4/3. So there we have an answer to this one. The next one's exercise 27. I'm going to leave that one for you, or we might work it in class. Thanks.